One, two, one, two. Okay. Hi guys, very good morning to you. Sorry, my microphone wasn't hooked up, and I just had to get it going. Right. Who have you got? Can you just, as usual, just announce yourself? So I've got your names for the register. So we've got, of those I haven't seen yet, we've got Amy. Very good morning to you. Good morning, Charlie. Good morning, Nick. Good morning, Ryan. Good morning, Harry. Good morning, Callum. Good morning, Declan.
Okay. Hi guys, very good morning to you.
And I have to.
I just had to get it going. Right. Who have we got? Can you just, as you
Right,
announce yourself? So I've got your name.
right. I just need to turn off the audio, otherwise you can hear me twice now. Anyway, who else have we got? We've got Ross and Luke. Very good morning to you. Anybody else? Please let me know. Somebody listening with you, same thing. Just let me know. So today we're gonna have, I think it's, if I remember right, we've got 3 sessions. So there's this presentation, and then 2 more presentations, and we're gonna cover all the criteria points which we need to cover for 315. And there's a little bit of repetition, 1 or 2 things which we haven't covered yet. But at the end of the day, you will have done the lot, and we've covered all the criteria, and you should have plenty of stuff to get on with. As usual, I'll upload the presentations. The presentations are going to be available here on YouTube, and hopefully everything goes okay. I've had problems with my internet connection. It went down. It seems to be stable now. So I was connecting the stream earlier, but I wasn't going live, and I was just looking at the number of frames getting dropped, and it was quite a lot. And yesterday I had a lot of problems with the connection, but it seems to be okay now. So we'll see how it goes, and then move on from there. Okay, so as I mentioned before, there's going to be a lot of repetition, but don't worry too much about it. It's going to be sweet and short, hopefully. We should be done in about an hour, so it's just about before your lunchtime, and we should be able to just move on. Okay, let's make a start. So this is about DC and AC machines. Yeah, so it's machines is a general term, and it's basically motors and generators. That's all we're looking at. You can see a couple of those pictures here, and again, when you look at DC machines, you've always got the commutator. When we look at AC machines, we've got slip rings, different ways of connecting machines. Some of the stuff, by the way, we've done in 308. But we're going to pick it up one more time here in 315. Okay, let's move on. So these are the criteria which we are covering. So it's 1.1 to 1.5. I leave them up for a short moment. So we've got DC machines and applications of DC machines, and then single-phase AC machines, a couple of applications, and then operating principle of of AC machines, 3-phase AC machines. I'm not sure whether we've covered this in this presentation. I think it's going to pick up on the next presentation, where we just look at 3-phase only and then work our way through. So correction, it's 1.1 to 1.4. I don't think 1.5 is in here. I tried to, or I was thinking of doing it, but I thought it's just too long, too confusing, so we do it separately. Right, please feel free to ask me questions whilst the presentation is going on. I've got my 3 screens here. One of them I'm monitoring the stream, the other one I'm monitoring what's coming out and making sure it's not stalling, but I can also see the chat room, and so I look every now and then on the chat room. If you've got a question, feel free to just type away whilst I'm talking, bearing in mind there's always this half a minute, 2-minute delay. Okay, so we start off with DC motors, and bear in mind, this is just a summary, so I'm just abbreviating a lot of stuff. Again, I can zoom in if you ask me a question, so please feel free to type anything in, and I will stop and look at the question. Okay, DC motors is one of the earliest motors which were developed. Makes sense as well. We had the photovoltaic pile in the 1700s. And they were just creating permanent DC sources, and they were sort of experimenting with little bits and motors and magnets and things like that. We've got a couple of graphics here. So we've got a permanent magnet you can see on either side. If you follow the mouse, we've got a north pole and a south pole. and then we push a current, and you can see this this wire, which is sort of indicated with this red bar here. We push a current through, and again, when you look at the graphic below, you can see how this wire goes all the way through. And as we push a current, a side effect is always going to be magnetism. Yeah. So again, when you take a piece of wire, push a current through, you always get two effects. One of them is heat, which is down to the DC resistance, and the other effect is magnetism. So you get like a rotating magnetic field around the wire where the current is flowing through. So that magnetism interacts with the permanent magnet, and it tries to line up with the north and the south pole. Yeah? So it pushes away, and as it is pushing away, we've got the commutator, which changes the current flow, and so the thing will turn around, and the current flow goes the other way around, and then suddenly there will be both magnets will repel the wires, and they will push them further, and so the thing goes round and round and round. The key is the commutator here, and you can see those brushes as well. And the commutator just changes the direction of current flow to keep the motion going for the DC motor to just go round and round and round and round and round. And anyway, that's how it works. So we've got permanent magnets, we've got the rotor coil, which is just this wire here. So in real life, you've got loads of these wires and loads of these gaps in the commutator to keep maximum momentum going, so that where the current flows is just sort of in the middle of this, between the north and the south pole, in the middle of the magnets, to keep maximum force operating on the rotor. The magnetism interacts with the permanent magnets. Rotor is moved. Commutator is used to change the direction of current flow, and that is to keep the motion going. Yeah. And the big thing about a DC motor is there's no fixed speed. There's a variable speed. It's determined on the amount of current you push through, the amount of magnetism in the permanent magnets, and obviously we have got permanent magnets, yeah, for little toy motors and stuff like that, where we don't need a lot of torque or anything like that. But we've got electric magnets as well, and electric magnets are far stronger than permanent magnets. So with electric magnets, we can generate a magnetic field well in excess of anything we can achieve with a permanent magnet. And so we can enhance the effect and get a lot more power out of a DC motor. So DC motors, in essence, are not very powerful compared to three-phase motors, to make the point at this stage. The ratio is about 1 to 10. Yeah? So if you've got a DC motor, and the DC motor is a certain size, and obviously you can push a lot of power through, you can push a lot of current through, and you can, vary the torque with the magnetism you generate and the amount of current you push through the rotor coils. But in general, the comparison for a three-phase motor compared to a DC motor, the amount of power is about 10 times, tenfold. Yeah. So it's for the same size, you get about 10 times more power out of it. And that's the reason why, for example, in cars and drones as well, where you've got like tiny motors, but you need to get as much power out of them as possible. You don't have DC motors in little drones, but you've actually got three-phase motors. Yeah, it's really, really bizarre, but the little drones, lightweight drones, it's all three-phase. So you've got like a tiny inverter and generating a three-phase current, and then you've got those coils and those motors, three-phase motors in the drone, and they all spin at precise speed and all that, and that's all controlled by little brain inside the drone and little inverter inside the drone. But also electric cars, even though they've got 400 volt DC batteries, they use three-phase motors to get maximum performance out of them. Right, let's move on. Any questions? Feel free to, as I said, to just jump in and in the chat room and leave a comment or a question or something, and then I'll go back, with a minute delay or something, and we'll clear this up. Anyway, that's the whole point of the live session here. So you can interrupt, and you're welcome to interrupt. Okay, DC motors, couple of questions. What is the purpose of the commutator? What happens to a piece of wire when a current flows through it? What happens when you place the north pole of the magnet near the north pole of another magnet? What are the main issues when a commutator is used as far as maintenance is concerned, and what can be used instead of permanent magnets? So okay, that's down to you now. Just fire off the answers in the chat room, and we'll then refer to them. I'll put kettle on, make sure the cat's okay, and then we'll look at the answers you've got for the questions. Okay. Couple of minutes for you to write an answer to those questions. Just looking at the stream. Stream is still okay. Yeah, everything seems to be fine at the moment, so should be okay. Have you got any answers? Not yet. Commutator reverses the flow of current. Good. Thanks, Ryan, for that. Hayden. 2 gets hotter is electrically charged, so can shock you. Okay. 2. Let's have a look. Yeah. So it can burn you as well. So if you've got a thin piece of wire, you push a lot of current through. It'll get hot. It can burn you. Yeah. Okay. Some more answers. 3 magnets repel. Okay. Some they repel. Thanks for that. For 3, that's right. It's very important as well. So that's the whole concept of the DC motor. So you get a magnetic field around the wire which repels against the magnet, the polarization of the magnet, and that's what turns it around, what gets the spinning motion going. Okay, number 4. Brazil produces magnetism. Yeah. Spot on. 2 effects, always magnetism and. It's, by the way, it's really tiny. So the magnetic field of a wire is tiny. It's not strong. It's strong enough that you can pick up a measurement. And obviously, as you increase the current flow and the magnetism increases, you get a bit of a response. Okay, number 2, electromagnetic field. Yeah, spot on. Actually, there's 3 effects as well. If you sort of get very nitty gritty on number 2. It's not just magnetism, but it's an electric field that's generated as well. So, and they are different. Magnetic field, electric field are different. They are at an angle of 90 degrees to one another, but and that's what we use for radio communications. Yeah, so we use the electric field, not the magnetic field, and that's just by alternating the flow and pushing it up and down. Right, let's have a look. Number 4. Number 4 is. What are the main issues when a commutator is used? One of them is maintenance, is wear. Okay, there's a few more issues with that. So one is maintenance, is wear and tear. So the brushes wear down. Okay, thanks for that, Brad. Number 5. 1, 2, 3. Number 5, electric magnets. Yeah, spot on, Brad. Ryan, grease and dirt, okay, for the commutator as well. Yeah, big problem. And if they get in there, then the performance of the whole thing goes down. Number 5, electromagnets, Hayden, spot on. Thank you. 4, burnout. Yes, potentially. The brushes. If it runs a little bit too fast and there are too many sparks going, you can have lots of problems. But the brushes wear down, that's a biggie, okay? So when you've got a DC motor, it's just a question of time until it wears out. So there's a given number of operating hours. Yeah? So it might be a couple of thousand operating hours, but eventually the motor is going to wear down and you have to change the brushes. And if it's not serviceable, you have to throw the motor away and get another one, like in toys and things like that. Okay. Any more advances on that? All right. Any advances on that? Okay. I think everything has been answered. Just to go through, purpose of commutator: change the direction of current flow, keep the motion going, make sure that the rotor always repels against the north pole and the south pole, so you get the motion going. Second question: what happens through a piece of wire when a current flows through it? You said it very well. You get number one is heat is generated, always the case. So as heat is generated, wire could potentially burn out. So this could happen to rotor coils as well if the current is too high. The flow through it. And the other one is a magnetic field is generated. And I think one of you says an electromagnetic field is generated, and that's spot on as well. So an electric field is generated as well. So if we alternate the electric field through a piece of wire, it actually starts transmitting. Yeah? So if you put an alternating signal through a piece of wire, like 1,000,000 times a second, you will actually get electromagnetic propagation, and that's what we use for radio communications. Place two north poles together from two different magnets, and they will repel. So that's the whole purpose or the whole concept of DC motor. What are the main issues when a commutator is used? So we had grease and dirt, which is a good point. Burnout is a good point. Wear and tear is a massive point. One thing which you didn't mention, but we're going to come to that as well. It generates sparks. Yeah. Sparks can be a big problem in industry. Bearing in mind you're working with flour, you get flour dust. So if you've got sparks generated, potentially it could cause an explosion. So it's not intrinsically safe. That's the proper term for that. What can be used instead of permanent magnets? And the answer is clear. It's just electromagnets. Okay. Right, let's move on. We've got DC motors and applications. So first of all, the DC motor's got a fairly low torque compared to some of the alternatives. It has got very high revs, and we can control the revs as well through the amount of magnetism. And this is sort of a weird thing when you use electromagnetic coils electromagnetic coils for a DC motor, and you control the current into the stator coil. So stator is the static stuff, so the coils instead of the magnet. So the lower the magnetism in the coils, the higher the revolutions. It's really, really interesting when you notice this. But the thing has got virtually no torque. So as soon as you put a load on it, the whole thing just stops down. Yeah? So it slows down quite dramatically. So as you increase the amount of magnetism, so that you make the magnet stronger, the revs reduce as you push current into the rotor, but you get more torque out of it. Yeah? So you've got more strength, more power to move stuff. Yeah? But the revs go down, and so you can play about, the way you connect the outer coils, the electromagnetic coils for the permanent magnetic field. And how you power them up, in comparison with the current through the rotor. So you can play about with the amount of torque and the revs you generate to do that. But and so DC motors are probably good for simple stuff, toys and possibly robotics as well, because you can use them for various things, or battery operated stuff. I mean, when you look at in the automotive industry, you've got your windows going up and down. That's a little DC motor, and and again, it makes sense because you don't want to mess about with an inverter and generating three-phase current and having lots of wiring. So you're looking for simple solutions, and those solutions kind of work. So you get like a high number of revs, put some gearing on it, and you get enough torque to move the window up and down. Use for small motors, toys, battery-operated equipment, starter motors. This is interesting as well. In your car, your starter motor, which is quite powerful because it has to turn the engine around. That's a DC motor, and you get like again, huge amount of current flows into it, so it can go to several hundred ampere for a short moment of time, and then otherwise low power-ups, power applications, where you're not too worried about efficiency and things like that. You just want something to move. The good thing about DC motors is that you've got variable speed, and you can control the speed through the current into the rotor and into the coils. Yeah. So and the torque as well. So you can play about with that a little bit. We're going to look at some of the connections as well later. You know how a DC motor is connected with electromagnets, and yeah, you can sort of see this. Okay, let's have a look at the next page. Types of DC machines. You've got a DC generator, a series motor, shunt motor, compound motor. So just follow the mouse, and again you can sort of see how they're all connected, yeah, and how you can mess about with the magnetic fields and the armatures where the rotor is, and the field is the field coils is normally called the stator or stator coils. They are static, hence the term stator. And there are various ways of doing this. One is shunt. You've got your DC supply, so you energize your electromagnets, and then you've got your armature. They're both connected, and then you've got, in this instance, a series excited DC motor. So you've got your field coils in series connected with the armature, and again they all perform slightly different. When you've got a permanent motor, a permanent magnet motor, DC motor. The beauty is you can just use them as a generator. And when you look at this configuration up here, that's just as a generator. So you've got a little crank here. You turn the crank round, and as you turn it round, you cut into those magnetic field lines, and the current is induced into the rotor. The current is then fed to the commutator, and the commutator then powers up the bulb in this instance. Yeah. And so you can create a DC current or a generator very simply by just using a toy motor. Yeah. So, I mean, you won't get much out of it, but you will get something out of it. And just one way of doing this. So, and that's the beauty as well. And you find, we're going to look at other methods as well in a minute, where very often a motor, it doesn't take much to turn a motor into a generator. That's very, very important to sort of bear in mind. Okay, next slide. What's the time? So we've got single-phase AC machines. So we're going to move over to AC machines. And again, when we talk machines, we talk about two bits. It could be a motor, it could be an alternator. That's a proper term for it, which is de facto like a generator. You know, it produces electricity. If you stick to the terminology, even though generator is a generic term and it's used for both AC power generation and DC power generation, if we are very precise with our language, then a machine that produces an alternating current is called an alternator, and a machine that produces a DC current is called a generator. Yeah. So that's strictly speaking, but here we go. I mean, they're just interchanged and used in any way. Okay, so first of all, we've got an alternator, and an alternator is something you've got in your car, and they are meant to work a little bit better than generators. I'm not sure why. The concept is pretty much the same. So you've got an alternator, then you've got and that's basically producing electricity in your car to charge your battery back up again, and then you've got a rectifier, which is just like 4 diodes put in a configuration, and it turns the alternating current into current that moves only in one direction and not in two directions. Yeah. Not from 0 to plus and then from 0 to minus, but just from 0 to plus all the time. But you still get this wavy waveform. Then normally you've got a capacitor or something like that to smooth it out a bit, and it's charging up your battery. So single-phase AC machines, we normally find they've got a small motor. Then we've got a fixed speed as well. It's very important. And so if you've got a pure AC induction motor, it's a fixed speed, which is determined by the frequency. We're going to look at the split-phase induction motor, capacitor start induction motor, and the universal motor as well. Now, a universal motor could be run off DC or AC, and you find also that a lot of AC motors, like in drills and in fans and things like that, they actually operate on a DC principle. Yeah, so some of them have got a slip ring and some of them have got even a commutator. So you rectify the AC and de facto you get some DC out of it, and you use a commutator instead. Okay, move on. Fixed speed machines. So we've got this number one, the speed is determined by the supply frequency, which you know from your three-phase motors, which we discussed in 308. So once the rotor is running, it will maintain momentum, so that's important as well. So a lot of fixed-speed machines, especially on AC, they are not, they can't start by themselves. So in theory, you would have to, when you've got a single-phase AC supply, you would have to kick them off, turn them around with the crank, and then once you turn them around and pick up some momentum, they will maintain momentum and they will run. And obviously, when you've got a fan, it's not like a fan to blow some air or something, and you've got a little AC motor on it. It's not a good idea to start spinning it by hand. It could chop off your fingers. So you have to do it. You have to have some means to let it start automatically, and I'm going to look at this in a moment. So to do this, this is the point number 1, 2, 3, 4. Let me just get the mouse down here. To do this, it needs an element of phase shift and starter windings. Yeah? So we have to have some means to generate a phase shift, which we don't need to do for a three-phase motor, but we need to do it for a single-phase AC motor to kick this into motion. And to do this, we have either got a capacitor, or they're called shading poles, or coils. Yeah? So we need to generate a little bit of phase shift to just kick it off, and once it kicks off, then it'll start running on its own. Okay, the next page. First of all, we're going to look at an alternator. That's the thing you will find inside your car. So that's an alternator, and it's got some rectifier diodes inside. Yeah, so it turns it into DC, from AC into DC, to charge up your battery. You tend to have a voltage regulator as well. So if you keep the things going by themselves and you don't have a regulator, you can get any voltages from 5, 6 volts all the way, depending how fast it runs, all the way up to 20, 30 volts. So there tends to be a voltage regulator in there to cut it off at about 14.1 volts or 13.8, somewhere between 13.8 and 14.1 to charge up your battery. Your battery runs at 12 volts. In order to charge it up, you need to have a voltage higher than the nominal open circuit voltage. That's considered to be about 13.8 to 14.1. If you provide 15 volts or more, it'll charge a lot faster, but it tends to not be very healthy for the batteries, so they don't last very long. Again, the rotor cuts through a magnetic field and the current is induced into its windings. So with the alternator, we've got some windings on the outside, and it sort of cut through, and then the rotor picks up some the magnetism. As it cuts through the magnetism, generates a current, and then it's got slip rings, and through the slip rings, the current is moved out into to your battery, into your systems, and then inside we've got rectifier diodes and a couple of capacitors and stuff like that to try and smooth it out and give you a clean output. Okay, this is how the alternator looks like, or the concept of an alternator. So we've got, you can see the slip rings here, and then we've got some magnetism on either side. So that's just a static magnetic field, not alternating but static. And then as this goes through the magnetic field and rotates around, it generates a current, and the current then is put out from the slip rings. The load would then be your car battery, but in our automotive context, we would have a rectifier as well to turn the AC waveform into DC. So all it does is the bottom cycle you see here, which goes below the 0 volt line, is put up to the top, and so what you would get is just like this wavy line, but enough to charge up your car battery. Right, next slide. We've got a single-phase AC motor. There's a little picture here, so we've talked a lot about it, but you can see what they look like. So if it's just a rotor, there's no connection between the rotor and anything else. So you don't have any slip rings or anything for a normal single-phase motor. So this will be the normal setup here. So you've got your windings where you put your AC current through, and then you've got a rotor which uses a squirrel cage. Same as with a three-phase motor, just a little squirrel cage. So the magnetism, which again, when you look back, it's generated through an AC signal, through an alternating current signal, which you see down here, should keep this into motion, but it needs to kick off first. So if it's static, it'll just lock in and the rotor is not going to move around. So what we have is we've got something which is called a start winding, and you can see this here in the second diagram. And so you've got your main winding, so these are the main coils, and then you've got a starter winding as well. So we put a capacitor in line, and then we've got our centrifugal switch. And the centrifugal switch is closed when the motor is not running or is running very slowly. And the capacitor will generate something like a phase shift. It's just a few degrees. So you've got your alternating signal coming from the main winding, generating some magnetism, and then you've got some magnetism generated, which is slightly offset, a few degrees offset, and that is enough to get this rotor to start spinning round, depending on how big the phase shift is. So if you manage to get anywhere up to 90 degrees or something, it'll be a lot faster. If you only get like a few degrees, it'll start spinning around, but it takes a lot longer for it to come up to speed. If it's 50 hertz, it's typical 3000 RPM. So it's an induction motor, so we've got no slip rings. It requires a capacitor or shaded pole with the starter winding, so we've got this here with the centrifugal switch. Again, when we talk about stuff like intrinsic safety, so that there aren't any sparks or anything like that, the problem is as soon as we've got a switch or a centrifugal switch in there, there's a potential of sparks happening. So a single-phase AC motor in an explosive environment is not a good idea. So because of the centrifugal switch we've got here. So it could potentially generate a spark and cause an explosion. So we really need to go back to an asynchronous three-phase motor, but we don't have any sparks and arcing or anything like that taking place for areas where it's likely to be explosive, like a flour mill or something, or a coal mine. So it requires a capacitor, and the other one is a shaded pole. We're going to look at this in a moment, and a starter winding to kick off the rotation. And the speed is fixed. Okay, it's determined by the frequency we put in. So if it's a 50 hertz supply, it's typically going to be about 3000 RPM. Obviously, we can use an inverter to change the speed as well. Okay, next one is we've got an AC motor with shaded poles, and what we get is our windings, and in our windings we've got these rings. Okay, you can see that all they are is just like little copper rings, but what they do is they generate a little bit of a phase shift. So as the coil is energized, you get a tiny bit of a delay for the shaded ring to be energized, and it might just be a fraction of a degree, maybe a degree or 1.5 degrees or something, but it's enough to start getting the thing to spin round. And the beauty is we don't have to have any centrifugal switches or anything like that, and so we can just keep it in, so there's no chance of any spark occurring when we've got a shaded pole motor. Problem is really low starting torque, and it takes quite a bit of time to come up to speed. Let me just go back. The problem with this array here, when we've got a capacitor, is if we keep the capacitor in line and the centrifugal switch doesn't work, like it doesn't open up or we don't have a centrifugal switch, it'll work and the rotor will continue to turn round. But what will happen is that the capacitor and the coils are heating up quite a bit, quite substantially, and that this could cause the capacitor to be destroyed, or the starter windings to heat up too much. Again, that may be an indicator as well when you've got a problem with a single-phase AC motor, and you use some thermography and the thing heats up. It might be that the centrifugal switch doesn't open, or doesn't work, or it's no longer functional. And that's the reason why the motor is heating up. It works fine, but it's just like really hot, and eventually the starter winding, so the capacitor, is gonna go, will be destroyed, and if that happens, the motor doesn't start anymore afterwards. So you would have to manually spin it around to keep it going or get it going. Okay, let's move on. Split phase induction motor. Again, we've got our rotor. It's a single phase. We've got our windings here, And what we have here, we've got our centrifugal switch, and we've just got a current, and we've got a starter coil and a different resistance. And so through, and again, don't sort of read too much into it, but whenever I've got a coil, I've got a resistance, and X stands for reactance. So the reactance is how the coil builds up a resistance to frequency. So if I put a DC signal through the coil, it's just like a straight piece of wire, and all I can measure is this resistance here. It's a DC resistance. As soon as I put an alternating current through a coil, I get something which is called an apparent resistance in addition to my normal resistance. So it behaves a little bit more sluggish, and the current struggles to get through it. And the higher the frequency, the more this effect. So if I've got different resistances and different coils, there's also something which affects the phase shift. So if I've got my main winding, I get a little bit of a phase shift there. And then if I've got a starter winding and I put this configuration in there, I may get a different phase shift if RA and XA are quite different to RM and XM. So if that is the case, I get a little bit of a phase shift, and the thing is going to turn around on its own due to the phase shift, the differences in phase shift. And then obviously once it's turning around, I need to turn off my starter windings. It's just a different way of doing the same thing. So instead of using a capacitor, you just use a different resistance or a different type of coil with a different resistance, DC resistance. Okay, you don't need to, if you don't understand this or it doesn't make sense to you, don't worry too much about it. It's just a different way of doing the same thing. In industry, what you will find is that most of the motors, single-phase motors, they will have a big capacitor in the terminal box. And when you open them up, you'll see your normal 3 terminals in there, and then you see this capacitor in there as well. And that is a giveaway. It's a single-phase motor. 3-phase motor doesn't need a starting capacitor. A single-phase motor needs one. And they can go down. That's a problem as well. So if they go down, they won't start anymore. And all you need to do is spend 50p on another capacitor and stick it back in again, and the thing works. Okay, next slide. Feel free to interrupt me if you've got questions. So we are now looking at the universal motor. And again, we've got an AC or DC supply, and you can see something like a commutator as well on this side here. So we have got our windings put together. This is how they are connected, the universal motors. And these motors will work on both. They will work on DC, they will work on AC. So hence the term universal motor. And it's just a configuration. That's the type of motor you would find in your Black & Decker drill, or a lot of funds will have this as well. Where else would you find them? Toys, maybe. So it's just a concept of a universal motor. Okay, move on. Application for single-phase machines. So we've got the alternator in the car, in your car. That's an AC machine. A power generator. So if you get like a petrol power generator, they will have an alternator in there. Fans, small motors, drills and rotary hand tools, and toys. And obviously in industry as well. Normally you would, if you've got a 3-phase supply, you would not use a single-phase motor because they're much more efficient. Again, an AC single-phase motor is about 1/10 to 1/5, depending how it's set up, to a same sized or equivalent sized 3-phase motor. So within industry, if you've got 3-phase available, your choice of motor would always be a 3-phase motor. In a domestic environment, most people don't have 3-phase available, so people would have like a single-phase motor. So that's typically when you, things like compressors or things like that for a small workshop. So most of the stuff would be based on single-phase. So small businesses, who are not in an industrial estate and they don't have access to 3-phase power, they would normally go for single-phase power, and they would need single-phase machines. Otherwise, in industry, and I would not place a bet, but would I place a bet? Maybe. But it's anyway. Uh, when you look at Hovis or Princess and you're looking for a single phase motor in the factory, you will probably struggle to find them, especially on lines and things like that. I think the majority of motors you're dealing with are all three phase. And feel free to correct me on that or to confirm what I said. But um, quick question: what's it like? I mean, can you easily find a single phase motor where you work, or is pretty much everything three phase? Okay, I'm gonna move on. Feel free to just write a quick comment on the list. Are we at the end? Yeah, we're at the end. Oh, that's good. It's 45 minutes. Okay, let me just dwell on this question a little bit. What's it like where you work? Have you got three-phase motors or AC motors? What's the majority of motors you're dealing with? Never worked on a single-phase motor, Brad. Let me just type this in. It's probably faster. Yeah, okay, Hayden. Yeah, that's what I would have expected. Yeah. A PMC as well. It's actually. I mean, we need to do some work on single-phase motors, and it's really hard to. I mean, in the PMC there isn't anyone. There isn't one I've found. So I have to get some from some other workshops to put them in there so you can see how they operate and how they work. But then again, you never know. You might come across one. Okay. Yeah. Okay. Thanks, Ryan, for that. Never worked on one either. Okay, that's what I expected, pretty much. Yeah. So single phase ones, and again, it's like the stuff that can go wrong with them is the centrifugal switch and the capacitor. They can go quite easy, and obviously the windings can go. And the capacitor to fix it is very cheap. It's a couple of quids, and if you have to use single phase motors and you ever throw some away, it's worthwhile to cannibalize them for the capacitors, store them away somewhere, and if you ever have another fault, to just swap them over. Okay, this is the last task for and this is a go away task. There's fundamental differences between AC machines and DC machines. Why is it possible to use a permanent magnet DC motor as a generator to produce electricity, but it's not possible with an AC single-phase induction motor? Okay, I want you to just a couple of bullet points to write this up. I'll email this out to you after this presentation. Again, usual stuff. Upload it to one file once you've done this. You can email it to me as well. And just sort of a little summary. I'm halfway through with the 309 assessments. I've come across a couple of problems. So if you get an email from me asking for certain bits and bobs, and they're clearly there, but I haven't seen them, please don't be angry with me. I'm using OpenOffice to read your documents. And what I've noticed is that sometimes when you put an image in or when you put certain formats in, it doesn't come up on OpenOffice. Yeah. So I don't see this. And it's happened to me before, today actually. I noticed 3 times. I was getting back to students about some stuff which wasn't there, but it was there. Yeah. I just haven't seen it because of OpenOffice, and I didn't realize that. I mean, the formatting sometimes is a little bit out, and you can't always see images. But there are other formats as well. It doesn't seem to pick up on it, so I wasn't aware of that. I'm now aware of it. Anyway, so that's one thing. Hopefully by the end of today, all the 319 stuff should all be done and dusted, and I'm through with that. And then I'll have a look at your 308 stuff and get back to you on all the 308 things. And then, when all this is done, we're going to focus on, or I'm going to focus on assessing 315. Right, that's all. What's the time? 11:30, so that's good time. The next session is going to be on at 2 o'clock. We'll be looking at three-phase motors, and then we've got one session right at the end of it, and this is all going into three-phase motors and a little bit more, and then we are done, and that's what we're going to do tomorrow. And then tomorrow afternoon we're going to look at the assignment and the written stuff you have to do, also the practical stuff. So some of the practical stuff, if you can do it at work, at all. I know it's going to be difficult with social distancing and whatever is happening now, but if you can do it at work, you're welcome to do it at work. If you can't, it's not a problem. When you come back to the PMC, we'll do it. I'm just trying to think. I don't think I've done it with you. We've done the 308 assessments, the practical ones. We'll do it when you come back at PMC, and if you have done it already, then obviously you're off the hook. And that's it. So I'll see you at 2 o'clock. I'll send you the link out shortly before, and then we'll carry on with this. Okay. Any questions before I end the stream? Okay, I'm just okay, that's fine. I'm just gonna wait half a minute or so, just in case any questions are coming through, and then I'll end the stream. I'll see you this afternoon then at 2 o'clock, and I'll email this task out to you in a minute, so you'll get it in your email. Okay. Okay. Right. Sounds good. I'll see you in the afternoon. So about 2 o'clock ish. Just make sure you're available, and then we carry on.